Hey all, so someone sent me an email asking for some clarification on conditional probability, and most of you, this seemed to be one of the topics that you most had questions about in class. So I thought instead of just sending a single email, I'd record a video going over it and the key points and a example each from tree diagram, two-way table, and Venn diagram using conditional probability. So first off, let's have a look at notation, so the symbology or how we write it. So a conditional probability is written something like this, okay? Where this straight vertical line here, nice and large vertical line, that's our condition. That's the symbol that implies it's conditional probability, and that means given. Okay, and it's given B has occurred. Okay, whatever that event is listed in the B spot, we're assuming, okay, we're going to assume that that has occurred. It's effectively mandatory. That must have happened. That's what we're being told in this problem. So we're trying to find the probability of A. So find the probability of A given that this B event has occurred. So that's our notation. So let's jump straight into, I think two-way table is the best way to show what this means off the bat. So let me build a quick two-way table. I need that. So let's go with, let's say some students, we're going to do a survey of year 8, and there's some students that like math and some that don't. Remembering that that little dash symbol means the opposite or the complementary event. So this code is M means likes maths, and M dash, as it's also referred to, or complement of M is doesn't like maths. And we'll use that same sort of idea, and we're going to go with, we're going to go with likes English or doesn't like English. So I'm just going to fill in some random numbers here. Let's go with 2, 3, 4, and 6. And then we'll add the totals up really quickly. So 2 and 4, 6, 3 and 6 is 9. We get 15. So in this case, we've surveyed 15 students. And there's all our totals put in. So there's our two-way table. Now, let me add another layer. Where's that gone? There we go. So I can draw over the top of this and then erase as need be. Okay, so let's have a look at the question. Probability that a student likes English given they don't like maths. Okay? So with any conditional probability, start with the condition. Let's start with this condition over here because we've been told that has to have occurred. So in this case, we're told, or we're being asked to find the probability that a student likes English given they don't like maths. So this condition, another way you can think of it is it reduces the sample space. So it reduces the sample space, or we can effectively think we get to ignore everything that doesn't meet that requirement. So in our case, instead of thinking of our original survey was 15 year 8 students, now all we care about is the students who don't like maths. That condition must have occurred. So we are going to ignore all those students because they liked maths. They don't meet our condition. So that means now we have different totals. All of that is ignored. So we can hopefully quite clearly see now, due to our condition, our total amount of students that we've surveyed is 9. So the conditional probability that a student likes English given they don't like maths, well, the total amount of outcomes or total amount of survey participants was 9, and the first term, get a different color, this first term that's our favorable or our desirable outcome. Okay, and we can see, well, how many of those actually liked English out of those 9 students that didn't like maths. We can see that there's 3 of them that did like English. So that's the conditional probability in a nutshell. Is the condition reduces our sample space. It reduces, we get to ignore everything out that doesn't meet that requirement. We could effectively delete it. Doesn't matter, doesn't exist anymore. We can ignore it for now, and then we recalculate our probability given our reduced sample space. So let me do some arrays in here, and I'll do another one showing visually what's occurring. Okay, let me increase my eraser size, make this a bit quicker. Okay. Here we go. So lay it out the same way. I want to find, I want to find the probability that a student likes maths given they like English. Okay. So let's look again, start with looking at our condition, our reduced sample space. We need students that like English. So we get to ignore everyone that doesn't meet that requirement. So all of these students who don't like English, don't care about them at the moment. All of that doesn't matter anymore. Okay? So my probability of maths given they like English, the total amount of survey participants that we now care about, we can see the total is now only 5. And our favourable outcome, okay, how many of them actually like maths? Well, they need to like maths, and there's only 2 of them. So the probability that a student like maths, given we know they already like English, is 2 out of 5. So I really like this idea of, on a test or working from a textbook or something, I wouldn't scribble over the top of your two-way table that you spent time making, but I would just hold my fingers over those columns that don't count anymore, and that helps me visualize my new totals or the condition. So that's how we do it with a two-way table. Let's have a go at a Venn diagram now. And we can set up a similar situation. Let me go back to my other layer. Let's set up the Venn diagram. And we'll do the maths English situation again. We'll use some different numbers. Okay, we've got maths, we've got English. And we'll say 7, 5, 8, 3. That's our spread in our Venn diagram. And we're going to do the exact same thing. We're going to exclude part of the sample, part of the population, given whatever conditions we have been given. So let's find the probability that a person likes English given, we'll start with this nice easy one. What's the probability they like English given they like maths? So straight away, okay, I need to start with the condition. They must like maths. So anyone that doesn't like maths, we no longer care about. They don't count in this survey. So inside the maths circle is good, but outside of that is no good. So all of these people, all of this survey outside of that maths circle is no good because they don't meet our condition. They must like maths. So we can see now how many total people exist in our survey. Well, that's the 7 plus the 5 that are still inside the maths circle. So that gives us a total of 12. Now we just need to look at what are our favourable outcomes. Well, we need our favourable outcome as the people that like English, and we can see that these 5 people in here, still, even though we scribbled over it, they are still inside the English circle. They're our favourable outcomes, so we get 5 out of 12. So that's all it is apply the condition, reduce your sample space or survey as needed, and then find the actual total and favourable outcomes numbers. So let me clear this layer and we'll do another one. Okay. Let's go a little bit harder. Let's go, what's the probability they like English given they don't like maths? Okay. So this is flipped on its head. Our condition here is that they don't like maths. Okay. So we need to look carefully at the Venn diagram and apply this don't like maths and do a bit of covering up or scribbling. So it's quite clear that these three people here that like neither, they don't like maths, so that's good. Okay. And also, these 8 people in here, they don't like maths, so they're good. But what about the 5 in here in the intersection, or these 7 in here? That both sets of those groups of people, they like maths, so we have to exclude them. So anything in the maths circle, because we don't want maths, we have to exclude all of these. Okay. So now we get to look at our reduced sample, our reduced survey, and we can see that the total amount of people still left is the 8 and the 3, so that's 11. And how many people actually meet our requirement, our favourable outcome, that they like English? Well, we can see that there's 8 people left that still like English. And that's our answer. Okay. So just like the two-way tables above, okay, I think it's best to visualize by blocking out anything that doesn't meet our conditional probability requirement. We get to block them out, we get to exclude them, and then look at what is left. So there's that was two two-way tables, that's 2 Venn diagram. Let's have a look at a tree diagram. So tree diagrams can be a bit varied in how it breaks down. So let's go with, we're picking red counters, and we'll say there's 6 in the bag, and blue counters, there is 4 in the bag, and we're going to do it without replacement. So let's build a tree diagram so we can get red or blue in our first pick, and then we pick our second counter, we can also get red or blue, red or blue. Now, since we're doing it without, well, let's put some probabilities in. Probability of getting a red is 6 out of 10. Probability of getting a blue is 4 out of 10. But since we're doing it without replacement, we're not putting that counter back. So we've taken a red out first. We've only got 5 left out of 9 total. We've taken red out first and then get a blue. There was still 4 left out of 9. This is going to be 6 out of 9, and this is going to be 3 out of 9. So there's our probabilities, and let's put in our outcomes or sample space. Blue, red, blue, blue. Okay. So there's our tree diagram. We could also calculate the probabilities of every branch, but I'm going to save a little bit of time here to talk about condition. Okay. So we're going to assume, let's jump straight in. What's the probability of getting red, red, given we got red first? Okay, in the first pick. What's the probability of getting red, red? So we know straight away we want this combination up here, red, red, but we're given the condition that we know we've already been given red first. Well, how do we deal with that? Well, we get to apply that condition. Anything that doesn't happen that meets this requirement, we get to exclude. Okay? So all of this tree diagram down here where we got blue first doesn't matter. Okay? And also, and this is a little bit of a weird thing on tree diagrams, we know that this 6 out of 10 chance of getting a red has actually already occurred as well. So that's occurred. So we don't even need to consider it. We know that that has happened. Tick. That's where we are. The only actual events that we're uncertain about being left is this bit up here. That's the only thing that we don't know yet. What's the probability, or what's going to happen? Are we going to get a red, or are we going to get a blue? And that's all we need to consider. We don't even need to look at the probabilities over here multiplied together. We just need to, because there's only these two branches left, well, the probability of getting red on the second go is 5 out of 9. So that is going to be 5 out of 9. Because I already know I've gotten red on the first go, so I don't need to worry about that 6 out of 10. It doesn't need to come into my calculations at all. So my only options left on my second go is either a 5 out of 9 red chance or a 4 out of 9 blue chance. And I want the red because I want red, so the probability is 5 out of 9. So let's do another one. What is the probability of getting, let's go blue, red, given I got a blue first. Okay. I got a blue first. And I'm putting the word first in here at the moment because that's pretty important, as you'll see in the next example. Okay. So same thing, I know I've gotten a blue first. So that means all of this over here, no good. Doesn't count. Doesn't exist anymore in our problem. Same, we know we've already gotten the blue first, so that doesn't exist anymore. So what are the two events that can happen? Well, I can either get a red on my second go at 6 out of 9, or I can get a blue on my second go in 3 out of 9. So what's the probability of getting blue-red given I've gotten blue first? Well, I need the red, so that means it's a 6 out of 9. And there's my answer. So the tree diagram like this, if we know something's already occurred first, then that's all there is. We get to scribble out all the other branches that don't matter, and we get to scribble out all the branches that have already happened. And lastly, probably the hardest one, and actually we haven't even done this in class. This is like high, almost year 10 work. So I'll leave it at that because I'm not going to ask a question like what I was just thinking of. I'll put it up for the sake of it. What's the probability of getting, let's say, red, given I know one of my picks is red? And that's actually really difficult because one of my picks is red means I need to include that combo or that combo or that combo. Could satisfy the sample. So either of those combos, we'd have to add together those probabilities. We'd have to do BR plus RB plus RR. That's our possible sample space. Any of those meet our condition requirements that one of your picks was red. But then what's the favorable outcome? Well, we need red. So you have to get the probability up the top up there, and you have to do a fraction divided by a fraction, which is some hard fraction work. But I'm not going to ask anything like that in the test. So that's it. I hope this video helps. It's gone for 18 minutes, but if one person needs it, probably a couple of you need it. If you have any questions, email me like normal. Thanks and bye.